Okay, so this is going to be the second big proof slash explanation sort of problem that could show up on the final. And so this one, we're going to be taking the derivative, a partial derivative, but the idea here is that we've only taken derivatives that go in the x direction or in the y direction. Now the idea is what's the slope if I give you some point on a surface, so like right there at P, and I want the slope in whatever direction I tell you. So the way that you define it is you say, okay, I'm going to pick a unit vector right here, u. So this is my unit vector, u. Okay, u. And I'm saying that's defined by AB. And so I want the slope of the tangent line on the surface that points in that direction, which is this slope of t up here. Okay, so in order to do that, basically this is what the problem's going to look like if you get this one on the final. And then we need to define a bunch of stuff before we can jump into the actual proof. And if you notice, the limit right here for that looks an awful lot like the limit definition for derivative that you've learned before. Okay, so let's see what we've got. Let's first define S. So let S be the surface. Oh, the pen's not working here. Hold on. All right, let's see if this works. Let S be the surface. Yeah, that works a little bit better. Defined by z equals f of xy. Okay. Let P be the point. X naught, y naught, and then the z value is whatever you get when you plug that into f. And then if you notice P prime, so I'll label it right here, x naught, y naught, f of x naught, y naught. And you notice P prime is just if I project that straight down onto the xy plane. So there's P prime. This is really going to be x naught, y naught, 0 right there. Let me shrink that down just a little bit because I'm going to fit some more stuff in there in a bit. And notice there's a prime next to the P there. Okay, so we'll define P prime. Let that be the point. X naught, y naught, 0. Notice there's this C here, the curve C, and it's stuck inside this yellow vertical plane. So, and it turns out that plane can essentially be oriented any way you want as long as it's vertical. So let's C be any curve on S, on the surface S, through P, through the point P, defined by a vertical plane through S. Okay. So C is the curve stuck in that plane and on S. Let's see, we still got T up here. So let T be the tangent to C, or we can say tangent line to C through P in the direction of some given unit vector u equaling a comma b. Notice u is stuck in the xy plane, so if you wanted a z, it'd be z equals 0. Okay. And then we know that the slope, so this is a definition here. The slope of tangent line T can be denoted as, and then this is a new notation, So it's capital D subscript u, which means the derivative in the direction of u of f. And then we're plugging in the point. It's at x naught, y naught. Okay, so this right here, that's a definition. So we're going to try and link that to this thing right here, that limit. Okay. Let's see, we still got some other stuff here. Q, point Q. So let Q be another point on C. Let me scroll down a little bit. Point on C. And Q prime be the projection of Q onto the xy plane. Okay, so Q prime is this point right here, right there. And we'll do one more let. All right, so let H, because notice there are H's up here in the limit, up at the top. And so I'm going to define H to be the magnitude of the vector P prime Q prime. Right? So this length right here from P prime to Q prime, not the whole length of U, just from P prime to Q prime, I'm calling H. Okay. So since, I'll put this in red since that matches. Since P prime Q prime and U equaling AB point the same direction, we can write P prime Q prime as H times vector U, so it's a scalar times U, which is the same as HA, HB. Okay, so if we go up to the diagram here, HA is the amount that PQ goes in the x direction. So this part right here is HA, and this part right here is HB. Okay. So let's see now, what does that mean? So then we can express Q prime, right? So let me cut and paste this because I'm scrolling a lot. Edit, copy, and then let's come back here, and I'll paste it down here. Whoop. Come on, let's select that. There we go. And I'll make this a little bit bigger, full page. All right, so let's define Q prime. So what this tells us, therefore, Q prime is going to be, so the x value for Q prime is really x naught plus HB. No, sorry, x naught plus HA, because Q matches up with that on the x-axis. So it's x naught here, and then this length was HA. So it's x naught plus HA. And then the y value was originally at y naught, and then I moved over HB units. So y naught plus HB. And then the z value is 0 there. And then we can figure out that means that Q has to be what you get. So the x and the y values are the same. So it's x naught plus HA, y naught plus HB. And then whatever you get when you plug that into F. So x naught plus HA, y naught plus HB. Okay. So I'm going to label that in the picture. Here's Q. That point is x naught plus HA, y naught plus HB, And then whatever you get when you plug that in, f of x naught plus ha, comma, y naught plus hb, parentheses, parentheses. All right, so there's Q. So what I want to do is related to single variable calculus. The way you get the slope of the tangent line in single variable, like let's say I want the slope, actually let me do a better one. Let's say I want the slope right here, right? Then in single variable calculus, what you actually do is you pick a point close by, whoops, sorry about that, and you make a secant line, and then you force this point to get closer to that point. So you take a limit, and usually you call that difference in the x values h. So you take the limit as h turns into 0, and as h turns into 0, this blue point gets closer and closer and closer, and that secant line starts to turn into a tangent line. And once h gets infinitely close to 0, you actually have the tangent line instead. So we're going to do the same sort of thing. So we're going to examine the secant line through P and Q. Okay, so let me sketch that in here. Let's do that right here. So there's PQ. Let me do that a little bit better. Whoa, why did that? Okay, one more time. There we go. Okay, so let's examine secant line PQ. So if we sketch a slope triangle in that vertical plane, the plane that's got P, Q, Q prime, and P prime in it, we can see at the run, the rise over run, right, the run is, and so right here, here's the slope triangle. So it comes down a little bit, and then it comes over a little bit. And if you notice, this part right here is exactly the same as this part right there, which was h. So that run is h. The run is h. Right? And then using the limit definition of derivative from single variable calculus, we can determine the slope of tangent line t by taking the slope of the secant PQ and letting h go to 0. So let h approach 0. So therefore, the slope of PQ, the slope of the secant, that's going to be the difference in the y values, or sorry, the z values really. So this, let's do the big one first. So this one minus this one, and then divided by the change in the run, which is h. So it's going to be f of x naught plus ha, comma, y naught plus hb, minus f of x naught y naught. So it's the change in z values divided by the change in the run there, right, or the run, which is h. So that's the slope of the secant. And so then the slope of the tangent is just when you let h go to 0. So therefore, slope of tangent at P in the direction of the little vector u is going to be the limit as h goes to 0. It's a terrible arrow. H goes to 0 of the same thing that's right here. So I'm just going to copy and paste right there. And we already decided from the definition up here that the slope of the tangent line there can also be denoted that way. So then this equals the derivative in the direction of u of f at x naught, y naught. And that's our proof right here. Now, it turns out I'm never going to actually make you take a derivative that way, but you need this definition in order to come up with the shortcut rules, kind of like how you have power rules and things like that. And there's a pretty simple shortcut for calculating derivatives in any direction in multivariable, but you need this limit definition in order to get that rule. So that's why we're covering it. Okay, hope that helps a little bit. And I'll see you guys whenever. Bye.